Hello everyone and welcome to FatalSec. In this video, you will discover a powerful technique commonly used by many in-app protection tools, which is about verifying the integrity of critical system libraries like libc.so, libart.so and so on. Basically, looking for integrity of system libraries is essential for ensuring the app security. Whether you are a developer, security researcher, or just an enthusiast, this tutorial will give you valuable insights into how modern in-app protectors uses integrity checks for detecting whether the environment is safe or not. So for the demonstration purpose, I am going to use a sample application which is called Inject Detect. Let me first show you how it looks like when the environment is clean. So on a clean environment, the application will show you this text message which says environment appears clean. Right now, let me start Frida server by going into ADB shell, taking super user permission, going to data local temp directory where I have the Frida server installed. There we go. And now if I spawn the application using Frida, and this is the package name of this application, you can see that it's detected few things. So basically the application has 4 or 5 different type of detections implemented. As you can see here, it's detecting a suspicious library in the linker. Then it has detected some suspicious keyword in maps file, followed by some suspicious keywords again in smaps file, followed by again some suspicious keyword in memory. Then it has detected some suspicious task names. And then finally you can see that it says library integrity check failed. This suggests that the system libraries such as libc.so is modified or got tampered, and indeed this is what happens when we run Frida server on Android. It basically tampers the .text section of various system libraries which these in-app protectors can detect. Another reason why these modern in-app protectors uses this technique is because if you try to create a new hook using interceptor.attach API of Frida on, let's say, open function, which is part of libc.so system library, it will inject its trampoline routine at that place, which modifies the .text section of the library. So by detecting these anomalies, these in-app protectors make sure that the environment is not safe to use and causes the application to crash. Alright, so our goal today is to simply bypass this kind of library integrity detection. So let's start with the analysis now. Let me just exit this Frida shell, clear this terminal, and as what we do with all other applications, our first step is to extract the APK. So here in this integrity check directory, I have already extracted the APK file from the device. So using APK tool, I am going to extract it like this, right? And once the extraction is done, you will get this new directory inject underscore detect underscore 1.0. And if you go inside this directory, you will find all the artifacts, resources which are packed into this APK file, right? So if you observe in this directory, we do have this lib directory, and inside this we are going to have ARM64 architecture directory, and inside this we are having our native library, right? So for simplicity and to keep this video concise, I will jump directly into the analysis of this native library, as that is where the actual detection occurs. However, if you are interested in exploring the Java layer, feel free to open the application using JADX GUI to view its decompiled code. Okay, but ultimately you will end up focusing on this native library part. Okay, so once we are into this lib arm64 directory, can you guess what's going to be our next step? Yes, pretty straightforward, right? We have to open this library using any disassembler for analysis. So I am going to use Ghidra disassembler this time. So here I already have it opened. Let me just import this library by going to file, import file, and here you can see we have our lib inject underscore detect native library, right? Okay, this is the import result summary. Let's just click OK. Now to start the analysis, all we have to do is simply double click on this native library which is already imported, and just click on yes to start the analysis in Ghidra. Leave all these options as it is for now and click on analyze. So once the analysis is done, we can start looking at its imported functions. So the approach is going to be simple. If you think logically, to detect if a system library has tampered with or modified, the application must first access that library, right? Since all the system libraries are stored in a file system, the application needs file system access to do this. Therefore, monitoring the imported functions, especially those which are related to file system access, gives us a good chance to identify the routine responsible for performing this integrity check. Okay, so let's first identify some functions from the import section, which you can find under this symbol tree window, imports, and all the imported symbols are visible under this external. All right, so we can see that we do have, okay, so in this list I can see this access function, which is responsible for accessing a file onto the file system. Then we have close, which basically closes the file handler once the file is opened. Similarly, we have fclose to close the open file. Then we have fopen. Then we have fstat, right? And also at the top you can see some of these functions which are starting from underscore underscore. So these are basically the wrapper functions. So here also we can see that we have a open function. This is a wrapper function, you can say, for open function. For now, let's just skip these wrapper functions and focus on the main ones. So let's first try to attach hook on these functions which we have identified and intercept their first argument, which contains the file path. For that, what I'm going to do is go back to the terminal. Let me just clear this out. Going back to the main directory, which is integrity check, right? And here let's just create a simple script and name it as integrity check.js. Okay, enter. Now, as most of you already know, to enable the hooks, we have this interceptor dot attach API of Frida, right? This basically takes two arguments. First one is the address of the function on which you want to attach the hook. So in this case, let's say we want to attach our first hook on open function. Now, in order to get the memory address of the open function, we have to call another API called module.findGlobalExport by name, and this API takes one argument, which is the name of the function. In this case, it's going to be open. So this API will simply return the memory address of the open function. Okay. Then the second argument is going to be a body, in which we can mention on enter callback. And inside this on enter callback, let's just simply put a log which says open, followed by the path it's trying to access, which is into the first argument. So to access the first argument, we have this args variable as part of this function's argument, right? So it's basically an array which contains all the arguments passed to the function we are trying to hook. In this case, we want to access the first argument of open function, and that we can access using the 0th index. Then we know that the open function's first argument is actually of type character pointer, which is nothing but a string. So we can read it as C string. Okay. Similarly, now let me just copy this code and paste it over here. And all I have to do now is change this function name from open to what was the another function we have identified, fopen, right? So let's just attach hook on the fopen, and fopen also takes its file path in its first argument. So we can leave this as it is. All right, then what else? I think we have also identified access function, right? So let's attach the hook on this access function as well. And access function also takes file path as its first argument. All right, so let's just leave it here for now and save this script. So now we have this integrity check script available. Let's now try to spawn the application and pass this script, which is integrity check.js, right? And in the logs, it can be observed that there are a lot of calls being made to these functions such as access, open, fopen, right? And also we can see that the application is trying to access proc self maps file using the fopen function. And open function, similarly, it's trying to access smaps file using fopen and open function. So these are actually coming from other detection mechanisms which are present in this application. We are particularly interested in the function which is trying to access any system library such as libc.so. So if you observe this output closely, there is no such function which is trying to access the system library. Okay, so this is expected as usually the functions used in detections are hardened or used indirectly. So if you don't find such function call from imports, your next step should be to check for SVC instructions, which is a stealthier way of calling file system functions. So let's quickly search for SVC instructions by going to the Ghidra disassembler. And in order to search for any specific instruction, what you can do is go to this search menu, click on program text, and then type your instruction. So we are looking for SVC instructions. Make sure to select all fields so that it will scan all the sections of the binary, and also make sure to select all blocks. Then click on search all, and you can see that it has not found any such instruction. Okay, interesting. Let's take a step back and again look into the imported functions. So you remember these wrapper functions I mentioned earlier? Let's now try to attach hook on these and see if we get any other useful information. And particularly, we are looking for the functions responsible for accessing the file system. So in this case, I can only see one such wrapper function, which is underscore underscore open underscore 2, right? So let's try to attach hook on this one just in case this is what the application is actually using during the detection. So again, going back to the terminal. For now, let me just exit this, clear this output, and again let's open our script integrity check.js. Inside this, I think now you know what we have to do. Let's just copy this and paste it, and instead of access function, this time we are going to attach our hook on this open2 function. Right here also in the log, let me just change the name, and open2 function also takes the file path which it's trying to open as the first parameter, so we can leave this part as it is. Let's save the script, launch the application again. All right, this time you can see that indeed our open2 function is being called at multiple places. So now we can see some other interesting artifacts being accessed, such as proc self memory, proc self task. So again, all these files are actually responsible or used by the application for detecting something. But down below you can see that it's trying to access libart.so, which is a system library. Similarly, it's trying to access libc.so, which is again the system library and the critical one, right? So because this application is not heavily obfuscated and does not employ advanced stealth techniques to conceal the use of these functions, we were able to identify this straightforwardly. Otherwise, it would have required more effort to pinpoint the exact function or instruction responsible for accessing this libc library. Now, earlier I told you that the application can detect whether these system libraries are modified or not, right? This means after accessing the libc library, it must be performing some kind of check to detect this anomaly, right? So let's now try to reverse this target application's native library like for real. So again, going back to Ghidra, what do you think we can do now? So we know that this open2 function is accessing libc. So in order to find the logic, we can try to see from where it is being called. And for that, we can have a look at its cross references. So Ghidra shows all the cross references to this function as a label over here. Okay. And as you can see, it's been accessed from these three places, and two of them are actually part of the open2 function itself. So let's just go to this, and here you can see that it's a thunk function. For those who are not aware what this thunk function is, it's a stub function which basically redirects the call to actual open2 function, as you can see here, right? And again, if you look at the cross references to these open2 function, you will see that it's being called from these three places. First one is from scan memory for keywords, another one is from check library integrity, and third one is from get symbol offset. Now this is very valuable information, and because this library is not properly obfuscated and most of the user defined symbols are visible in this library, that's why you are able to see these function names as it is. So based on these function names, we can simply skip this scan memory for keywords. Instead, let's focus on this check library integrity function. By looking at the name of this function, indeed it's something which might be doing this system library detection, right? Now, one important thing to point out is that in this library, we can actually see the user defined function names. But in real world applications, that's usually not the case. So you will need to rely on your static and dynamic analysis skills to track down the right function. And don't worry if you can't find it right away, because later on in this video, I will show you a dynamic analysis technique that will help you out once we understand how this function works. Alright, now let's go inside this check library integrity function and let me show you how its control flow graph looks like. So if you click on this graph icon at the top, it will show you the nice CFG, and that's how it's look like. Not a very big function, I would say, so it should be pretty easy to understand. So let's start analyzing it from the very first basic block, which is this one. And here these first few instructions are actually part of function's prologue. So these instructions are used to set up the function in memory, like allocating the stack, storing the function arguments, and things like that. So let's just skip over it, and in the next block we can see that it's calling a function called iscrc32 table initialized, followed by a conditional branch. What this means is that if this crc32 table is initialized, then it will go directly to the next basic block, that is this one. Okay, otherwise it will come over here and it will try to generate a new crc32 table. Okay, so for now, just keep all these things I am telling you in the small cache of your mind. Moving on to this basic block now, and over here we can see that it's trying to make a call to another user defined function with the name find memory mapping. And just by looking at its name, I am assuming that it's trying to access proc self maps file, which stores all the memory mapping of the libraries loaded by our target application. So this proc self maps or memory mappings file basically contains information such as where the library is loaded into the memory, what is the file path from where it is loaded, and things like that. Actually, I can also show it to you just in case you are curious. So let me go back to terminal. Let's just clear this out and let me just go into ADB shell. Our application is already up and running, so what I can do is I can get the process name of this application using ps command. So this is the process name, and you can actually read the proc maps file simply using cat proc followed by the process id followed by maps, and it says permission denied. That's because we are not running as root. So let's get root access, and now let's get this file. Okay, so over here you can see how memory mappings actually looks like. So here you can see that the system libraries and whatever the library which are required by this application, all of that is actually mapped into the memory, and it shows you the memory location as well, like from this address to this address this library is loaded, and what are the permissions, like the page permissions, whether this particular library is readable, executable, and things like that. Okay, now let's again go back to the Ghidra disassembly, and just to be sure that this function is indeed doing what I have just showed you, let's quickly go inside this function by double clicking on it. Okay, and yep, this is again in the first basic block, all basic setup is being done. And in the next basic block, immediately you can see that indeed it's trying to access proc self maps file using fopen function. So remember, in the Frida output we saw that fopen function was trying to call proc maps file, so probably this piece of code was responsible for that. Okay, Now, if you want to understand how this function is working, feel free to analyze its disassembly. It's pretty straightforward. But what I can tell you is that it's actually trying to read that proc maps file line by line, okay, and trying to parse its memory range, including the permissions as well as the file path. So here in this basic block, basically it's trying to call scanf function on the already open proc maps files, right? And then it's trying to parse that mapping file line by line in this format. Okay, so for now, let's just go back to our main function, which was this one, check library integrity. So whatever the value returned by this find memory mapping function, that will be stored onto the stack, and then using this LDR instruction, it's loading that result into this W8 register, which it is then comparing to decide which path to take. We can see that in this block, it's calling our wrapper function, which is underscore underscore open to, right? So when we hook this function in our Frida script, probably from here it was called, and in the hook we saw that it's accessing libc library. So it's important to understand now what this check integrity function is doing from here on. So right after this open to function call, you can see that there is a conditional branch again, test bit on non-zero. What it will do is based on the result of the open to function, whether it's able to access a libc.so file or not, it will return 0 or -1. -1 in case there is an error in accessing libc.so file. If that is the case, then it will take this path, and I think by following this path, yep, you can see that in this basic block it's simply printing that failed to open, which makes sense, right? So let's go back and see what's going on if everything goes well with open to function and this path is being followed. So in this basic block, basically again it's trying to call another imported function called fstat, and this fstat function basically takes file descriptor returned by this open to function as its argument. So this will make sure that the library accessed by this open to function is indeed accessible and present. So basically, as an attacker, you might think that simply by changing the path to this open to function to a non-existing file path, we could bypass this check. But that is not going to be the case over here, because firstly, there is a condition mentioned over here. So if you pass a file path which does not actually exist on the file system, then it will immediately take this path and show this error message, fail to open, right? But let's say somehow you manage to bypass this check, then there is another check which is making sure that that file path exists. If not, then it will show this fail to get file error message. I would say that this is really a solid implementation. Okay, so let's follow along. If everything goes well with fstat function, this basic block will execute next. And in this basic block, we have another imported function call being made, which is mmap. So this imported function is responsible for creating a new mapping into the memory. Basically, it will create a new memory space and map the bytes into that memory area. In this case, it's mapping the bytes from libc.so file into the memory. And once the mapping is done, then it's closing the open file using this close function. All right, so far so good. And then we can see this. So over here, you can observe that there is a loop running over these basic blocks, right? And in this loop, if you observe here, we have two function calls being made to crc32 function. Now remember, in the beginning of this check library integrity routine, we saw a function call which was checking whether crc32 table is initialized or not, right? This one. Well, that crc32 table is required by these two crc32 functions to perform cyclic redundancy check. It's a hashing algorithm which is used to detect any changes into the data. And if you see right after these two crc32 function calls, we have a comparison instruction followed by a conditional branch, right? So as per ARM64 calling convention, if you remember, the result returned by a function that will be stored into X0 or W0 register, right? So if you observe here, after this CRC32 function call, it's moving the result of W0 register into W22. So what we can say is that now W22 register is containing the result of this CRC32 function call, right? Similarly, over here, when this CRC32 function is called, its result is present in W0 register, right? And now the result of this CRC32 function, which is in this W0 register, that is being compared to the value present in W22 register, which is nothing but the result of this CRC32 function. So here, using this comparison instruction, we can say that it's basically trying to compare the results of these two CRC32 functions, right? And based on that, it's deciding whether to execute this block or not. And in this block, basically it says that executable section is modified. So this is basically the core logic where all the checking is being done. So let's understand what exactly is being checked by these CRC32 functions. For that, let me switch to decompiler mode because I think it will be easier to explain, as well as it will be easier for you to understand what's happening here. Alright, so here we have the decompiled code of this check in library integrity function. And here we have our two CRC32 functions which are being called, right? So in the first CRC32 function, we can observe that it takes two parameters. The first parameter is actually this variable called pyvar5 identified by Ghidra, and this variable is nothing but the variable containing the result of mmap function call, right? And by looking at the definition of the mmap function returns a pointer to the memory location where it has mapped the data into the memory, right? So basically this pyvar5 variable is pointing to the memory location where this mmap function has mapped the data. And if you monitor this argument of mmap function, which is ivar2, this argument is actually containing the result of open2 function. And we already know by now that this open2 function is actually trying to access libc.so library from the file system, right? Which means this ivar2 is containing the file handler of libc.so, which is stored on the disk. So what we can say now is that this mmap function is actually mapping the data or the bytes of libc.so system library, which is stored on the disk, into the memory, and that particular memory address is stored into this pyvar5 variable, which is then passed to this crc32 function. So in short, this first crc32 function is actually calculating the hash on the libc library which is stored on the disk, right? Then in the next crc32 function, it's actually taking sstack208 as its argument. So this sstack208 variable is nothing but a variable which was passed in find memory mapping function. And also, if you observe here, the way it is being accessed in the crc32 function is through this dot operator followed by some array indexing, right? So this is usually the way how we access structures, right? So what we can say is that this sstack208 variable is a type of structure which is passed to find memory mapping, and we have already analyzed this find memory mapping function and identified that it's basically passing procmaps file, right, which is containing the information such as memory range or the memory addresses where the library is loaded into the memory, the permissions followed by the file path of the library, right? So what we can say for this sstack208 variable is that it's a structure which is having all these different fields and it's storing all this information. So here in this crc32 function, it's basically trying to calculate hash on the data or the bytes of the native library which is already loaded into the memory by the operating system. So now in the first crc32, we have the hash of the libc system library which is on the disk, and then in the second crc32 function, we have the hash of the libc system library which is in the memory. And then it's simply comparing the result of these two CRC32 function and deciding whether the executable segment is modified or not. Now, if you remember what I said earlier, that when we hook functions using Frida, it injects a trampoline routine, which actually modifies the bytes into the loaded library. So in case you are hooking open function, which obviously resides in libc.so library, the instruction responsible for calling open will be modified. This means that libc library in memory has now different bytes as compared to the one which is on the file system. And this is what triggers this detection. Now let's think about how we can bypass this. I think it's pretty straightforward now. All we have to do is somehow pass the same set of data or bytes to these two CRC32 function, on which it will calculate the hash and compare them. In this case, because the function names are visible, it became easy to identify the core logic and these two CRC32 functions. But in real world application, this won't be the case. So let me show you a generic way instead. As we have identified that open2 function is being used to open libc.so file directly from the file system, the process then accesses the already loaded libc.so in memory by passing the memory mappings. So if we manage to supply this open2 function with the exact same file that resides in the memory after attaching the hooks, then the result of CRC32 calculation will match, which effectively bypasses the integrity check. So the question now is how we get the libc.so from the memory and pass it to this open2 function. For that, we first have to dump the libc.so library from the memory and store it somewhere on the file system. And then using Frida hook on open2 function, we can pass the path to this dumped libc.so file. So let's first begin with the dumping of libc.so. For that, again, I am going to use Frida. So let me go back to the terminal. Again, open our integrity check script, enter. Let's create a new function called dump module. Okay. Here, let me just create a variable called so name, and in this, I will mention the name of the library which I want to target, which is libc.so, right? Then in order to get the information about this loaded libc.so library, what I can do is I can use a Frida API called process.getModule by name, and this takes one argument which is the name of the module which I have already stored in this so name variable, and this will return a module object which contains the metadata or the information about the loaded module, such as the name of the module, the base address of the module, size of the module. So let me just store this into this module variable. Okay, then just for troubleshooting purpose, I'm going to put this log, which is going to say found module.name. Okay, followed by another log which says base address. So this will tell us where this module is actually loaded into the memory, and then let's just also print the size of the loaded module, which is module.size. Okay, now let me just create a try catch block just to be sure that our script does not crash. Okay, and let me just put a log in the catch block which says error followed by the exception. All right, now let's come to the try block. Now in order to dump the library from the memory, what I'm going to do is simply I'm going to read the bytes from the memory address where libc library is loaded. So this module.base will tell me where libc.so library is present in the memory, and this module.size will tell me up to how many bytes I have to dump, right? So for that, let me just create a buffer variable where all the bytes will be stored from the memory, and it's going to be dumped from the base address. I'm going to read it as byte array, and here I have to tell the size. So this simple one line will basically dump all the bytes starting from this address all the way up to this, right? So let me just put another log which says successfully read module.size byte. Again, these are just for troubleshooting purpose in case anything fails at runtime. Now, once I have the bytes in this buffer variable, what I have to do is write it into a file. So for that, I am going to create this output path variable in which I am going to write these bytes. So let's just save these bytes into a file in the same directory where the application is installed due to app sandboxing restrictions. So if you try to store it somewhere else, then the app would need to request storage permission, which this application currently does not ask for, making that approach more complicated and requires extra work. So what we can do instead is just simply store these bytes into a file in the same app data directory, which is /data/data/ the name of the package, which is this one. And then what you can use is the name of the module followed by the extension, which is .so. Alright, now in order to write these bytes into the file, what I can do is I can make use of this file object. So this file constructor takes output path as its first argument followed by the permissions. So I want to write it into a file by opening that file as writable. Okay. Now what will happen is that this file constructor will give me a file handler which is pointed out by this file variable. So this is currently an empty file. I have to write the bytes. So for that, using this file handler, I am going to write my actual buffer, and then I can simply close this file, and that's pretty much it. Here again, for troubleshooting purpose, I am going to put a log which says dumped successfully at output path, right? So this is our dump module function. Let's save it. Now, before actually dumping the library, it's crucial to ensure that the hooks you have enabled are active. Specifically, the functions you intend to hook from libc.so must already be enabled. Why? Because when you dump the library, it will contain all the patched instructions injected by the Frida hooks. Otherwise, even if you dump the library, it will not match the bytes of libc.so which is loaded into the memory after enabling the hooks, causing the integrity check to fail again. Right? So for now, if you see our script, we have these hooks already enabled. And then when we dump the module, the instructions responsible for calling these functions in libc.so will be patched with the trampoline function of Frida. So if you add any new hook after dumping the library, that information will not be present into the dumped library, right? And this is not something which we really want. Alright, so we have all our hooks enabled or defined into this integrity check script already. What we can do now is launch the application again, enter. Okay, now what we can do is simply call our dump module function in order to dump the file from the memory. And as you can see, the script found the module with the name libc.so. It has already found the base address and it has successfully dumped the file into this path, right? So one thing which I did wrong was that there is no need to add additional .so into the output path. The file name or the module name already contains .so, but anyways, it's still a valid libc.so file which we have dumped. So this should work. Let's just exit it from here, and to be sure that it's dumped at correct place, let's go to this directory from adb shell. And here, yep, indeed we got this libc.so.so. And also what you can do is run file command on it just to be sure that it's a valid elf. And yes, it is. Okay, perfect. Let's just come out of adb shell, clear this terminal. And all we have to do now is modify the argument which is being passed to this open2 function, right? Let's just comment this interceptor.attach and replace this whole implementation of open2 function. That way it will make sure that whenever open2 function is called, every time our custom implementation will run. Okay, so for that we have another API called interceptor.replace. Basically, it creates a new function into the memory and replaces the pointer in the PLT table with this one. So just keep in mind that whenever you try to replace any argument of any function, it's better to use interceptor.replace instead of interceptor.attach. Okay. So over here, this replace API again takes two arguments. First one is the address of the function which you want to replace. So that we can get using module.find global export by name. Here we can mention underscore open2, right? Then as the second argument, it takes a native callback, which we can define using new native callback. So it basically takes two arguments. First one is the path name pointer and second one is the flags. Okay, all right. So inside this, I think it's pretty straightforward. Now, what we can do is, first of all, we can read the existing value of the open2 function, which is into this path name pointer. As we already know that the first argument of open2 function is of type character pointer, which is nothing but a string. So we can read it as C string. Okay, and then we can put a log just to be sure that we have captured the correct argument. One2 called with path, right? Now we have to put a condition to make sure that it will replace only when libc library is being accessed. So for that we can use if statement, and in the path variable we have the path which this open2 function is trying to access. So if this path has libc.so, then only we will replace the argument. So here we can mention our new path. This will be nothing but the path where we have dumped the libc.so library in the previous step, right? Which was under data package name and then libc.so.so, right? Now let allocate this string into the memory using memory.allocate utf8 string API, and here we can pass this new path string, and this will return a memory pointer which is containing this string. So let's name it as new path pointer variable. Okay, again for troubleshooting purpose, let me just put a log which is going to say open2 redirecting path to new path, right? And now we have to return the original implementation of open2 function. So for that, what I have to do is, before starting off this interceptor dot replace, I need to store the original function pointer where the actual definition of open2 function exists. So let me just create this original open2 variable new native function, and this is going to contain the original definition of open2 function. So again I need to pass the actual address of open2 function over here, followed by the data types of its arguments. So that would be int, pointer, int. Okay, so now we have the original implementation of the open2 function, and what I am going to do now is simply I am going to return this original open2 function, and in this original open2 function I will pass the modified arguments which are new path pointer and the flags. And as a fallback mechanism, so in case open2 function is trying to access some other system library or some other file, we want to make sure that things work as expected, so we have to return this original open2 function. And this time, instead of passing the new path pointer, I think I made a typo here, it's actually new path, right? So yeah, in this case we don't want to replace the original argument, so let's just pass the original variables as it is, right? And here all that is left is the argument types: pointer, followed by integer. Okay, I think we are pretty much done. So what this code will do is whenever open2 function is called, it will execute this implementation instead of the original one. So first of all, it will fetch the original path name and store it into this path variable. Then it will check whether that path contains libc.so, because that is what we want to replace, right? So if that is the case, then it will manipulate it with a new path which is pointing to the dumped library which we did in the previous step, and then it will call the original open2 function with the modified argument, right? So let's just save this script and hopefully everything will work as expected. So let me launch the application again, enter, and yep, in the application you can see now that we are not getting that error message which says library integrity failed. Also in the logs you can see that open2 function was called with libc.so and then it immediately redirected to this path. Perfect. So we have managed to evade library integrity check detection based on comparison of CRC32 checksum between on disk libc.so and in memory libc.so. So as you can see now, all our hooks which we have applied are working as expected, right? And the application is not able to detect those hooks which are applied on the system library. So the same approach you can use for other system libraries as well. Okay, so this being said, I hope you enjoyed this video and learned something new. Feel free to comment in the comments section in case you have any questions or doubts. You can also connect with me and become a part of our FatalSec community by joining our Telegram group link, which I have mentioned in the description box. Thanks, and I will see you in the next video soon.